There's no question today that quantum mechanics has completely changed how people think about the universe. I think the discovery of quantum mechanics is thought of as something of a paradigm shift, a revolutionary turning point in the history of physics. But I wonder if the people first discovering quantum mechanics really recognized how revolutionary their discoveries would be. What is it really like to live through such a crazy moment in physics? In this episode of Why This Universe, we talk about how quantum mechanics was first discovered, and we dive into how the big players really felt about the theory that they were uncovering. My name is Shalma.
And I'm Dan.
And you're listening to Why This Universe.
Yeah, I don't think you can appreciate how different quantum physics is unless you compare it directly to the thing that came before it.
That's Dan Hooper, theoretical physicist and regular Why This Universe co-host.
So we call pre-quantum physics, we call it classical physics. And this was basically established by, it was more complicated than this, but roughly by Isaac Newton a couple hundred years before the quantum revolution. And in classical physics, objects are at one place at one time. They move in an entirely predictable way under various kinds of forces like gravity. And this paradigm did really, really well for like 200 years. It just kept explaining more and more observations. You could expand upon it to include things like electricity and magnetism and heat as those things were understood. But still, it just continued to work. And one of the really attractive features about it is it conforms to our intuition. If you kind of just picture how you think things in the world will move and behave and act, it's pretty close to what you'll find in a classical physics textbook. You definitely can't say that about quantum physics.
So for 200 years, classical physics was the paradigm that physics worked under. But then there was a moment that seemed to change everything.
And it had to do with the nature of light. So in 1900, physicists thought they understood light pretty well. They thought it was an electromagnetic wave, and in a sense, that's correct. That we haven't changed that part of the story. And they knew that if you take things with electric charge and accelerate it, it radiates light, and that's true of anything with electric charge, which means any kind of atom or molecule or any kind of known matter would radiate light. And you could basically, from first principles, calculate the spectrum of light that a kind of material should radiate. And this was done in 1896 by Wilhelm Wien. And that spectrum that he predicted is called Wien's law, or Wien apostrophe S law. And everyone just kind of thought this would be the right answer. And it worked pretty well. It works really well at high frequencies. But around 1900, measurements started to show that at low frequencies, the Wien's law prediction just isn't manifest in nature. It's just not right. And this is really weird, right? Like I said before, this was basically derived from first principles. And it's hard to see what could have gone wrong in Wien's calculation. But something clearly did, because the observations didn't agree with it.
And this disagreement between Wien's law and experiment is often taught in quantum mechanics classes as the observation that broke the paradigm of classical physics. But for those actually living through this, it probably wasn't all that obvious at this point that this disagreement would be so significant.
If we went back and did a survey of physicists in 1900 and asked them what they thought of this, I think you'd probably not find many who were really worried about this problem. But that's the thing about hindsight, is you can look back and say, oh, that's where it all broke. But as a physicist in the year 2020, I can point to all sorts of anomalies that are being discussed and published and stuff. And probably the vast majority of those anomalies are just going to be explained away. Maybe the measurement was bad. Maybe there's something about it that we did wrong in the analysis. Maybe there'll be some very mundane explanation. Almost always that's true. So it's really hard to tell at the time and place which anomalies are going to be mundane and have boring answers or boring resolutions, and which ones are going to lead to something as revolutionary as quantum physics.
So anyway, Wien's problem was eventually picked up by a big shot physicist at the time, a German man named Max Planck.
And he took the measurements of this spectra of light and kind of reverse engineered a formula. He just tried a bunch of functions until he got one that fit. And that thing is called the Planck spectrum to this day. And then he took that and kind of deduced backwards. He reverse engineered, well, if this is the right equation, what could I assume differently than Wien did to explain why the equation's the way it is? He tried a bunch of different things, but he ultimately settled on the hypothesis that objects like pieces of matter are only able to radiate light in quantities that's proportional to the frequency of that light. So if I have a chunk of matter and I heat it up and it radiates light, the pieces of light will be radiated in chunks of energy proportional to the frequency of that light. And the proportionality constant is still to this day called Planck's constant. E equals Planck's constant times frequency.
So to summarize, Max Planck reverse engineered a solution to Wien's law, which worked by suggesting that an object can only radiate light at discrete energies, rather than being able to radiate at any energy in a continuum. But he didn't take this interpretation of light too seriously.
I don't think people thought that this was the biggest deal in the last 100 years of physics, which I think it's fair to say it was, or something like that, or at least among it's on a short list of the biggest deals in the last 100 years of physics at that point. But they thought it had something to do with the nature of matter and something about the way that matter vibrated and radiated light. They didn't think it had anything to do with the nature of light itself.
To realize exactly what Planck's solution meant for the nature of light, it took someone else. And that person was Albert Einstein.
So let me paint a picture. So it's 1905. Einstein is 25 years old. He's just a few years out of college. He had spent 2 years looking for a job teaching physics, or even better, doing research, and none of those jobs came together. And he eventually settled for a job in the Swiss Patent Office. And he wasn't a big deal in the Swiss Patent Office either. His title was third-class technical assistant, and there is no fourth class. Like, that is the very, very lowest level patent office job you could have. And like, he's making some middling progress towards his PhD while he's working at the patent office at the University of Zurich. But, it's 1905 now. He still hasn't completed his degree. He certainly hasn't made a name for himself. If you had to guess where in the world the next revolution in physics was going to come for, this would not have been your guess. This was way, way, way down on the very bottom of your list of reasonable guesses for that. But still, in 1905, it happened. He put out 4 separate papers, all of which were revolutionary in different ways, changing physics forever. He had a paper on Brownian motion that basically provided the first real empirical evidence that atoms exist. It's a pretty big deal on its own. He had 2 other papers that introduced the key concepts of special relativity. General relativity would take 10 more years, but he'd eventually do that as well. And then the 4th really key paper of 1905 was his paper on the photoelectric effect, which is the one we're going to talk about now.
So like Dan said earlier, Max Planck interpreted his results to mean that something about the nature of matter caused it to emit light with these discrete energy steps.
Einstein took a more radical interpretation of some of this data. And he said that it's not about the matter. It's not about how the stuff's being radiated or vibrating or anything like this, but it's about the nature of light itself. He said that light comes in discrete pieces, particles, if you will. He called them quanta. Today, we'd call these things photons, or particles of light. And he said that the individual photons, or light quanta, had an amount of energy proportional to their frequency. So it's the same equation Max Planck used, but with a really different interpretation.
And in his photoelectric effect paper of 1905, Einstein used his interpretation to explain experimental results that nobody previously understood.
He pointed to the phenomena of fluorescence, And it was known that certain materials, when you radiate light on them, they would emit fluorescence. And it was already known at the time that the frequency of the fluorescence was always lower than the incoming light. This was something known as Stokes' rule, and no one had an explanation for why that was the case. It was just like a fact, but no explanation had been offered. And Einstein said, well, if the light comes in these parts, then a photon hits a molecule and imparts a certain amount of energy to it. And just by conservation of energy, the light that comes out has to have less energy and therefore be lower frequency. So it just kind of followed from the hypothesis of light quanta that Stokes' rule should be true. So that's his first argument. And then he goes on to the main part of his paper, which involves this experiment called the photoelectric effect. So it had been known for a while that when you shine light onto a metal surface, this can cause energetic electrons to be emitted from the metal. And if you hook a metal plate like this up to an electrical circuit, you can generate an electrical current this way by shining the light onto the metal. This is called a photocurrent. And everyone expected the amount of photocurrent you generate this way would have to do with how much energy in light you shine on the metal. The more energy, the more total amount of energy, the more photocurrent. But what had been experimentally shown in just a few years earlier than Einstein's paper was that it didn't have to do with just the amount of energy, but the frequency of the light. You could only generate a photocurrent with high frequency light. And no one had an explanation. But Einstein said, well, this makes all the sense in the world if light comes in quanta or photons. A low energy photon can hit one of those atoms in the metal, but it won't liberate the electron, it won't free it, so you don't generate any photocurrent. But a higher energy photon can hit that same atom, that same electron, and break it off and generate a photocurrent. So there's a kind of a threshold. You need a minimum amount of frequency to generate photocurrent. And once you exceed that threshold, then the number of photons above that threshold determines the amount of photocurrent you generate. So it all kind of holds together if you take Planck's law seriously as a statement about the nature of light itself.
So what's really so weird about Einstein's observations was that light, which we usually think of as a wave, seems to have this particle property when you think of it as being made up of discrete pieces called quanta. And the behavior of light can really only be understood if we accept this dual reality, that light is, at once, both a wave and a particle.
I don't think really anybody believed it at the time, though. I mean, maybe Einstein did, but you can find very, very few examples of physicists in 1905, 6, 7 who really thought that light came in quanta. That seemed to be maybe a useful abstraction or something, but it would be years before it became really widely accepted.
And surely, around 15 years after Einstein wrote his paper, he won the 1921 Nobel Prize in Physics. But that was only after years of experimental evidence that kept showing that this weird wave-particle duality of light really is true.
So the problem that people had in accepting that light could be a particle and a wave just has to do with what we think waves are in classical physics. So if I talk about a water wave or a vibration on a string or a sound wave, these waves are all like collective behavior. They make sense because the water is made up of a lot of smaller parts. In some places, you could have more stuff than other places, or the sound wave is just a pressure wave moving through a medium, and there's a bunch of molecules moving through. It's a collective behavior that manifests itself as a wave. But if you're taking a photon and say this is a indivisible thing, this is one object and it is the smallest piece of light you can have, there's no collective behavior there. That one thing is a wave. How can an indivisible thing be a wave? That was what made it so hard for so many physicists to accept Einstein's radical proposal.
And at the same time physicists were grappling with the wave-particle duality of light, some physicists were thinking a lot about the nature of the atom. And so around 1908 to 1913, Ernest Rutherford's experiments showed that the atom is made up of a dense charged core, which we call the nucleus, surrounded by orbiting negative charges, which we now know are electrons. And the common picture was to think of electrons orbiting the nucleus like planets orbiting around a star.
But this model was known to have some pretty big fatal flaws. First of all, if you did have something like a solar system and those electrons were zipping around a positively charged nucleus, they as they're being accelerated in their motion, they should radiate a lot of light, lose a lot of energy, and just come crashing into the nucleus in no time. So atoms should be almost instantly unstable. And then the second problem is, like, we had observed all of these spectral lines from different kinds of atoms. So if you take hydrogen and heat it up and put it in a lab and measure the spectrum from it, on top of the kind of Planck's law kind of spectrum that you get these very specific bright emission at certain frequencies, and no one knew how to explain it. That was a total mystery. No one knew anything about atoms that could help to explain this. So it was clear that the solar system model can't be the whole story. And in 1913, the Danish physicist Niels Bohr came up with an explanation for these two issues. But to do it, he had to assume something very radical, something kind of similar to what Einstein had been promoting. But whereas Einstein said that light, which is a wave, is also a particle, Niels Bohr said electrons, which are particles, are also waves. So to explain what this means, let's just picture a vibrating string or something, like a guitar string. We know that there are only specific configurations, like specific notes that you can play on a guitar string. What Niels Bohr did, he said that electrons are the same way. In these circles around, these circular orbits around the proton, you have to have a standing wave configuration for the electron to exist in it, according to him. This led to a series of harmonics or energy levels that the electron could be in. And in each of these states had a different amount of energy. So let's just say, for example, that an electron's in the second energy state. It can spontaneously move to the lowest energy state, the first energy state, and give off a very specific kind of light, a very specific frequency light. And it turns out that all of these transitions give you the spectral lines that have been observed. So you can solve the problem there that way. And also you solve the stability problem because the lowest energy state, that first energy state, is the lowest one. That's the bottom. There's nowhere to go lower energy than that. So once you get an electron in that lowest energy state, it just stays there. So if you start thinking about electrons not only as particles, which of course they are, but also as waves that can experience interference, then you can explain at least two big problems that people had trouble explaining about the atom.
And so not only are photons both waves and particles, but Bohr showed that electrons are too. And so you can't help but think, is everything both a wave and a particle? And the answer is, yeah. So
the first person to really advocate that idea was a young PhD student in France, Louis de Broglie. He just said, well, Einstein says that light is a particle and a wave, and Bohr says that electrons are both a wave and a particle. Maybe just everything is. Absolutely everything. And he even had this equation saying that the wavelength of something is the Planck's constant, that number that came up in the 1905 stuff, divided by whatever object you're talking about, its momentum. And I don't know about you, but I don't feel like I'm a wave. I don't feel very wavy. I don't experience me or stuff around me undergoing wave-like interference very often. So this seems really weird.
Sometimes I feel pretty wavy. So.
Yeah. But picture some macroscopic object. My go-to macroscopic object is a baseball. So just picture a baseball. And the smaller its momentum it is, the bigger its wavelength will be. So let's pick a really small momentum. Let's make it move like a millimeter a century. Okay, so it's barely moving at all. That thing will have a wavelength of 10 to the minus 20 meters. You just can't notice that. That's not very wavy. Okay, so that's kind of the explanation that de Broglie gave for why we don't seem to notice the wave-like nature of macroscopic objects like baseballs. But if you take an electron in some atom somewhere, electrons are moving really fast. around atoms, and they're very light. The typical electron is moving at like 20 million miles per hour or something like this around an atom. And it turns out that if you use de Broglie's equation, you find that the wavelength of an atom like that will be like 10 to the minus 10 meters, which is about the size of an atom. So if you look at an atom, unlike that baseball I described, its wavelength is about its size, or about the volume of space that it occupies. So interference is going to be super obvious in the environment of an atom. These you can't picture it as like a planet moving around a star like the solar system model, but instead that electron is something kind of smeared out over that whole volume, undergoing interference with itself and with other electrons.
Right. Those are the kind of orbitals you learn about in like high school chemistry or something.
Exactly. Yeah. So that was 1924. And within only a few years, like 1927 or so, they had done things like the double slit experiment with electrons and showed that electrons actually do undergo interference. So electrons do in the laboratory behave as waves, just like light does.
So let's move forward to the 1920s.
We have stuff like the Schrödinger equation, which gets written down and published in 1925 by Erwin Schrödinger. Huge progress is being made by these new kind of young physicists, Paul Dirac and Werner Heisenberg. Contributions from people like Pauli and Born, and list goes on and on. They're going to all these great conferences and exchanging ideas in all these famous ways and stuff. And like around this time, it's becoming clear that the math is working. The experiments that are being conducted are, finding the results that the math is predicting. So they're on to something. Everybody agrees like they're making progress, and this can't be totally wrong. But no one agrees about what any of it means. In particular, what does it mean for, something to like an electron to be a wave? Like, what are we really describing here? Like, again, we're this question of one object, singular, indivisible object, but it's a wave. How do you have a wave without collective behavior? And in 1926, a proposal, super radical proposal, but one that is approximately what we use today, was proposed by the physicist Max Born.
So at this point, it was known that you could describe a quantum system with something known as a wave function. So a wave function is a function spread over space, or whatever parameter space you're looking at. Say, if you're considering the momentum of a particle, it would be spread over momentums. And at each point, there's an amplitude corresponding to that state. But people didn't exactly know the physical meaning of the wave function because it could take on complex values, numbers with the imaginary unit I, equal to the square root of -1, which doesn't have much physical meaning. So Born's rule came and gave more meaning to the wave function by saying that if you square the wave function, you get the probability of finding the particle at that particular state.
What this seems to imply is that electrons aren't in one place at one time. Electrons don't have one velocity at one time. They don't carry a singular quantity of energy, but kind of have a range of energies. And when things happen, they happen smeared out over a range of times. One way that this is manifest is in Heisenberg's uncertainty principle, which says that the more you know about an object's momentum, the less you can even in principle know about its position, and vice versa. And the same is true for the amount of energy carried by something and the time at which it carries that energy, and vice versa. So, and it's important to appreciate that Heisenberg wasn't telling you something about your ignorance. He was telling you something about the objects themselves. It just built into the laws of quantum physics that things like position and momentum and energy and time aren't singularly well-defined. Anything that exists in nature has a variety of, or a range of these quantities at any given time, if you want to think about it that way.
So let's take a moment to appreciate just how different all this quantum stuff is from what we previously thought about physics. We can no longer certainly say that an object is in X location with Y speed. An object can be in multiple places at once by having its wave function be in a superposition of different states. And you could think of the implications of this on something as fundamental as whether our universe is deterministic, whether it follows one well-defined and predictable path through time.
So in classical physics, the theory is entirely deterministic. What I mean by that is if you use Newton's laws and said I'm going to tell you the location and speed or velocity of every particle in the universe with infinite precision, and I gave you an infinitely powerful computer, you could calculate how everything in the world would be at any point in the future, at any point in the past. They completely follow from those initial conditions. So there's nothing about the future that in principle is unknowable. I mean, it might be in practice impossible to have a computer that strong or to have measurements that are that good. But at least in principle, classical physics is entirely deterministic. But quantum physics is different. If I have something that's in a superposition of states, when I do a measurement, I find one or the other, one particular value of its whatever location or energy or time or momentum, and I can't predict in any deterministic way which value I'll measure. I can only calculate the probabilities. So quantum mechanics is like fundamentally different in its probabilistic nature.
So now let's talk about how the people who discovered quantum mechanics felt about their discoveries. Just because they were the ones to make the discoveries doesn't mean that they were necessarily ready to accept them. And one of the most classic examples of this is Einstein himself.
Einstein had a lot of complicated thoughts and feelings about quantum mechanics. Sometimes I think it's a little bit misunderstood, and frankly, I'm not sure he was often all that clear about what his objections were, but definitely by the 1920s, he was, doing, verbal combat with his colleagues over how to think about quantum mechanics. And yes, he definitely thought that quantum mechanics, as it was being thought about at the time, and basically the way we think about it now, must be substantively incomplete. It couldn't be the whole story. Even though, he played a huge part in starting off this whole particle wave duality thing with this photoelectric effect paper, he saw where that pointed and said, no, I can't accept that weird of a universe. He insisted on a philosophical position known as scientific realism. He said there's a singular, well-defined universe out there, and from that, we can do experiments to find out what's going on in that universe. But he wasn't willing to take he was very reluctant to accept the idea that an electron could be in a superposition of different states, or that there would be no way that you could predict what an electron was going to do, even if you knew everything about some initial state of the universe. He's often quoted as insisting that God does not play dice with the universe. And this is kind of what he's getting at with this. Although his feelings about this were probably more complicated than any one catchphrase can encapsulate.
And of course, Einstein wasn't the only important figure in this process. There were also other physicists with other perspectives.
So I think Bohr came to represent the kind of conventional quantum mechanics interpretation, what we call the Copenhagen interpretation, where things are really in these superpositions until you measure them and the wave functions collapse and they take on specific values of the measured quantity. But so he definitely was advocating for that sort of position. He talked about this complementarity idea a lot, where different physical quantities were complementary to others. So in the same sense that Heisenberg said you can't know the position of momentum at the same time, he called those complementary quantities, and he kind of built up a philosophy around that. Other people like Schrodinger were kind of closer to Einstein in outlook. Erwin Schrodinger, he looked at the situation, and by the mid-30s, he was writing things saying, well, if you really believe the kind of Copenhagen picture, the Niels Bohr picture, then there are a lot of really weird things you have to accept. And he proposed the Schrodinger cat thought experiment to kind of illustrate this. And it was pretty clear that he and Einstein thought there were things going on in quantum physics that hadn't been appreciated yet. But I think in the past, 50 years or something, people have just kind of gotten used to the idea that quantum mechanics doesn't conform to Einstein's vision of scientific realism. The real universe, the way it actually works, is just different from what he was prepared to accept.
Yeah, I wonder how this influenced like a new generation of physicists to an extent. Because I definitely like my attraction to physics when I was like in high school and reading physics books was these kinds of things that weren't intuitive and didn't seem obvious. But like by the time I was reading it, we were pretty confident in quantum mechanics. So things like that like really attracted me to physics. And I wonder if like because of that we have like a more open-minded generation or something like that.
If a 20-year-old version of me encountered physics like it was in, I don't know, 1880 or something, I wouldn't have become a physicist. I think that's kind of what you're saying, right? The stuff that attracts people like you and me to physics in 2020 are things like, relativity and quantum mechanics and black holes and other weird things that are super counterintuitive, and they're definitely the opposite of what happens when you roll things down inclined planes. Yeah. So yeah, but you can find physicists with all sorts of personalities, right? And some are attracted to, and some find there to be a lot of elegance and beauty in ordinary 1880 classical physics. We're just not two of them.
Thank you for tuning in to this episode of Why This Universe. We are now available on every podcast streaming service that I'm aware of, Apple Podcasts, Spotify, YouTube, and you can find us on Twitter at twitter.com/whythisuniverse. Please leave reviews and comments if you like the show. We really appreciate hearing people's feedback. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.